Hi everyone. This week we're talking about multiverses. I've made a couple little jokes on this slide with my titles. I think that in the end what we'll find is that multiverses are really interesting, but there's not much reason to think that they exist. There are lots of different ways, it turns out, to come up with theories of multiverses. Multiverse, by the way, is a portmanteau, a combination of two different words, where we are combining together the words multiple and universes to get multiverses. So the basic idea of a multiverse, and this applies to all of the different versions that we'll be looking at today, is that you have more than one universe. To say that something is a universe is to say that they're causally separated from one another, that they don't interact, that they're entirely individual, separate things, but that they nevertheless exist. So different accounts of the multiverse will have different numbers of universes in them. Some of them have infinite universes, some of them have just a couple. We'll talk about all the different ways, or at least several different ways that people have talked about multiverses in the past. Interestingly, it turns out that even since ancient times, people have been thinking about the possibility of alternative worlds, worlds besides our own. If you think back to the Aztec account of the above and the below, especially that version that had several, right? What was it, 13 different levels? Each of those levels of the universe is kind of like a universe of its own, because they're separate from each other, the laws are different. Now the Aztecs didn't really talk about laws of nature, right? But they talked about things being more divine or supernatural on other realms than in this one. And different kinds of things live there. It's a different kind of environment, all of that. Perhaps the reason to think that this is a multiverse is that those are several different realms where things exist, and yet they're all part of one totality. So the multiverse would be the totality, that the whole of the above and below taken together, and each level would be its own universe. Now, that's not really how the Aztecs or any of the other ancient American cultures conceived of the above and the below, but it's at least leaning in that direction, and so we can begin to see this idea in the past. I should pause and just mention that this word world is used pretty often to mean universe when we're talking about multiple worlds or multiple universes. Those words mean the same thing. Sometimes the word world just refers to the earth, but then there are other senses where it has a cosmological meaning. And that's the one that we'll be using today when we talk about multiple worlds. In essence, the idea of alternative universes starts from this question: what if things were different? What if things are different than they are? What if instead of gravity being attractive, it was repulsive? Right? You can imagine a new kind of universe if you do that. Or what if the electrical charge was a little bit weaker? Right? You get a whole new kind of universe out of that kind of speculation. You could even ask, what would the universe be like if my father didn't exist? Or what if my grandfather didn't exist? How would this universe, or how would a universe be different if that were one of its preconditions? And so you can kind of imagine alternatives to this universe. Then the question is, what is the status of those alternative universes? Do they actually exist, or are they just fictions that exist in our minds, that just are imaginings? Well, to get at that question, let's talk about the possible and the actual. If you ever read Aristotle, you'll see Aristotle spend a lot of time talking about potential and actual. Aristotle thinks of all change in the universe as involving potentiality transforming into actuality. So that's an interesting model, an interesting way of thinking about it. And there are a couple of things we can say about the possible and the actual to try to distinguish one from the other. Certainly anything that is actual, anything that really exists, is possible, because impossible things can't exist. That's what it means to be impossible, right? Is that you can't exist if you're impossible. So something like a square circle is impossible, or a square with 3 sides, that's not possible. So those things can't exist. All right? So things that can exist, things that could exist, we can call those possible. And then amongst the things that are possible are the ones that are actual. So the actual is a subset of the possible, right? So if you have 2 circles, the bigger one is the possibilities, and inside it is a smaller one of the actualities. Now notice that on that account, or that way of understanding it, the fact that something is possible doesn't give us reason to think that it's also actual. the possibility itself is not reason or evidence for thinking that the thing is actual. So we're going to need to find other kinds of evidence to prove actuality. The possibility doesn't even make something probable, right? Even if it seems highly plausible, that doesn't mean that it's probable. So be sure to be careful when you're reasoning about these kinds of issues, because it's pretty easy to slip up and let your excitement of these weird and interesting ideas make you believe that something is actual when it's merely possible. There's a German philosopher named Wilhelm Gottfried Leibniz. If you're interested, we'll study him in my early modern philosophy class. And one of the things that Leibniz is most famous for is a book called the Theodicy. The Theodicy, or the general project of theodicy, in not just his book, but any theodicy, is to try to explain how it is that the world can be the way it is, and yet there be an all-good, all-powerful God. So Leibniz is trying to solve the problem of evil in philosophy of religion. So the problem of evil in philosophy of religion is that, look, God's supposed to be, at least on the Christian understanding, right, infinitely wise, infinitely powerful, infinitely good. So it has all knowledge, all power, and perfect goodness. How in the world could a being like that create a universe like this one, where there's all kinds of pain and suffering and injustice, and a lot of it seems to be entirely trivial and doesn't need to exist? Well, Leibniz's argument is that God can make any possible world. God can't make an impossible world. But from amongst all of those possible universes, God chooses just one of them. So possible in this context just means logically consistent, doesn't contain any contradictions. So a world is logically consistent if you can describe it and you don't end up with two statements that say the opposite of each other. All right, so any world that can be described that way, Leibniz will call a possible world. Now, clearly there are zillions of possible worlds, right? We can imagine a world just like this one, except the whole thing has moved 1 foot to the left. Or we can imagine a world just like this one, except the sun is just a tiny fraction less bright, or a little bit more bright, or anything else, right? So just make all these tiny little differences and you're going to make a zillion different new worlds that are possible in some sense. All right, so for Leibniz, the range of possible worlds is actually going to be huge, probably infinite. There's probably going to be an infinite number of impossible worlds too, but certainly an infinite number of possible worlds. And this is going a little bit beyond what in the early modern period in philosophy we call the conceivability criterion. It was a popular idea at this time to say that anything that we can conceive or think of without forming a contradiction is possible. So I can think of a golden mountain, even though no mountain is actually fully made of gold. That's a possible thing because I conceive of it and there is no contradiction in my conception. On the other hand, I can't conceive of a square circle. I can put the words together next to each other in a sentence, but it doesn't mean anything because it's self-contradictory, right? A circle has one boundary, it doesn't have four sides. So I can't have a single object that has four sides and only one side, right? So that's a contradiction. So the early moderns say that anything that you can conceive, anything you can think of, is possible. And if you conceive of something but it involves a contradiction, then that thing is impossible. But Leibniz wouldn't stop there. There are going to be additional possible worlds that aren't conceivable by minds like ours. So a more powerful rational mind might be able to think of things that humans can't imagine. All right, and those will also be possible worlds in the ensemble of possible worlds that Leibniz is considering. So these possible worlds are outside of our own. They're other universes. They're not our own universe. They're another version of our universe or some other version of a universe. All right, could end up being quite different from this one, but at the very least, it's not connected to this universe. Right, it's entirely separate. Now, this does raise an interesting question. Where do these possibilities exist? And there are two kinds of answers that people have given about this. One is to say, well, they just exist as logical or imaginary entities. You could describe that metaphorically as they exist in logical space, right? There's not really a logical space, but kind of like a space, you could imagine arranging all of the different possible worlds in a conceptual or intellectual kind of realm. That doesn't actually exist, of course. It's just pure conception, pure imagination, right? And you could say that, well, possible worlds exist in this possibility space as mere logical possibilities. But there's another way to think of this too, and that is to imagine that every possible world, or some subset of those possible worlds, actually exists. In other words, that some of these worlds that can be conceived of without contradiction actually exist in some elsewhere, right? Not just far away in our universe, but entirely outside of our universe, whatever that means. All right, now you can't really specify that because we don't know what that means to be outside of our universe. All of our experience is in this universe. But maybe that's not a contradiction to say outside of the universe or in another universe. So that's where we would imagine these possible worlds to exist. Now for Leibniz, God only makes one universe, the very best one. And the reason for that is that logic binds God in the sense that God can't do anything that's contradictory. God can't create a stone that's too heavy for him to lift, or God can't create a square circle or a bachelor who's married, right? Those things can't exist. They're impossible because when you think of them, you think of a contradiction. So Leibniz thinks that God is bound by logic in that way. God's also bound by, so you could say God is bound by his nature as a rational being, or an intelligent being. And Leibniz goes on to say that God is also bound by having this property of infinite goodness. And that means that since God is perfect, God won't do anything that is less good than it could be. All right, so it's not that God can make a perfect universe, because for Leibniz, that thing is not a possible world. Somehow or other, and he doesn't really ever explain how this is, he just says it must be the case that God can't make a perfect universe because it must involve a contradiction for such a thing to exist. Now his best argument here is that God can't make a perfect universe because he wants to give us free will, and the universes in which human beings have free will are better than those universes where humans don't have free will. And somehow or other, free will comes along with evil and pain, and so God can't make a perfect universe. So out of all of those universes that he could make, where humans have free will, he chose the best one, the one with the least amount of pain and suffering, and created that one. Okay. Now, why didn't God create any other universes? Well, according to Leibniz, that would make God inferior. God would be choosing something that is less good, and therefore there's less reason to produce it, and so God would be violating the principle of sufficient reason, which a purely rational being would never do. Okay, so there's lots of assumptions built into this. It's purely speculation. The argument actually is probably not very good because it ignores the problem of natural evil. It kind of explains away the problem of moral evil, the evil that we do to each other with our free will. But it doesn't explain why, for example, there were fires in Australia in their summer of 2019 in which 1 billion animals were killed. Right? That's suffering and death. That has nothing to do with human free will. So God clearly created that universe, right, if there is a God. So how can Leibniz say that that's the best world, right? It doesn't seem to make sense for an all-good God who's benevolent to cause so much suffering for no reason. So the problem of natural evil, as it's called, isn't resolved by the free will claim, and Leibniz doesn't get around it in his Theodicy. Well, those sort of philosophy of religion details aside, and I teach a philosophy of religion class too, if you're interested in that, we'll go into a lot more detail. But for the present, for our purposes today, we're going to have to move on and just think of Leibniz as setting up for us the possibility that there are many worlds, or that there are possible worlds that exist in a possibility space. And those worlds might also be actual. Okay, so we'll see in as we get to the work from more recent physics that this idea persists and it's been modified in various ways. Before we get to the modern stuff, though, let's talk about Aristotle just for a moment. You'll remember in the geocentric model, Aristotle has the Earth at the center, surrounded by water, air, fire, and then the superlunary sphere containing quintessence and all the planets, and then finally it's bounded by the sphere of the stars. Now this is a bounded universe, which is to say it's finite, it has an edge. And all things considered, it's pretty small, right? We could imagine a bigger one. Certainly in modern cosmology, we imagine a much bigger universe. So it's a fairly natural thing if you are considering a finite, bounded, small universe like Aristotle's to ask, well, what's outside of it? And in Roman times, Lucretius, a very important philosopher who wrote a book called On the Nature of Things, De Rerum Natura, which is definitely worth reading if you're interested in the history of philosophy. And he imagines throwing a spear at the sphere of the fixed stars, right? It's supposed to be the boundary, the edge. And he says, well, what would happen to this sphere? Would it puncture the sphere of the stars and keep going? In which case there's space outside the sphere of the stars, and the sphere of the stars is not a boundary. Or it's going to bounce off. Why would it bounce off? What's there? It's just an edge of space. So that doesn't seem to make sense either. So Lucretius comes up with an argument for thinking that the universe must actually be infinite, that beyond some apparent boundary, the universe continues. So you can imagine combining the Aristotelian idea and the Lucretian idea. Instead of coming up with just one universe, a geocentric universe that's infinite, you can imagine a whole bunch of small universes like balls nested together in an orange crate kind of arrangement in 3D, right? And you'd have all of these bounded small universes kind of collected together. No reason that couldn't be, right? That's one way to have multiple universes. There's no evidence that anything like that exists, but it's certainly a natural thought given the Aristotelian cosmology. In the late 1800s, a woodcut of this image an engraving of this was printed. This is a colored version of it. It was just in black and white in the original, but I think the color makes more clear what's going on, especially on a screen. And you can see here's somebody who's been taking a walk in the wilderness, and he's come across the edge of the world, where the sphere of the fixed stars butts up against the flat disk of the Earth. At least that's the picture that this drawing is giving us. And he pokes his head through and wants to see what's on the other side. And what he sees back there is amazing, right? It's all the stuff that runs the universe. Well, you can imagine going beyond that, right? And going even further, going to the edge of that. Well, what if you stick your head through that thing? So any kind of bounded or small universe is going to have an edge. It's hard to explain why the edge would be there. And then it's natural to think, well, what's outside of it? Now, there are some ways of getting around that problem in sort of contemporary higher dimensional geometries, but we're not going to get into that today. All right, so still speaking about the ancient period, let's talk about time for a minute, because time is another way that you could end up with multiverses, as we'll see. There was an idea that was common to many ancient civilizations, including the Mayans, the Egyptians, the Greeks, and the Indians, that is from India, not American Indians, but from India. And they all proposed an idea that's very similar, that namely that everything that has happened will happen again. Everything that's happening now will happen again in the future. My wife just read this fantasy novel, a series of novels called The Wheel of Time. If you're into that, it's apparently pretty good, although it's extremely long. And the idea is that sort of the same families of characters, the same things keep happening to them, right? And the same political struggles and the same environmental disasters, and there's a long cycle, but then things start repeating themselves. And this was represented in ancient Greece by this strange fictional animal here, the Ouroboros, a snake eating its tail. For some reason, the medieval manuscript illustrator put feet on this snake, but there you go. Maybe it's a dragon eating its tail. That might make more sense. The idea of the dragon eating its tail, though, is that as it digests its tail, it grows, and it eats a little bit more of its tail, and it grows, and eats a little bit more of its tail, and it's this endless cycle, right? So it's just going to keep going around and around, and that's meant to be an analogy for time, that something's happening now, time will go on in a circular fashion, and later it's going to happen again. Now, there's something interesting about this, right? It talks about fate in a way, right? That things are just going to happen. You don't have any control over them. Maybe that's helpful. Maybe that relieves of us a certain amount of anxiety because, well, we don't really have any control anyway, so just try to enjoy the ride, something like that. It also points to tragedy, right? That terrible things are going to happen no matter how hard we try. So this is an interesting model. There are other ways of implementing this. It doesn't have to be just a pure circle, right? You could have this exact repetition, and you then would have an eternity of time by just infinitely repeating some finite cycle of time. Or you could, instead of having exact repetition, just have analogous repetition. So that instead of the very same thing happening the next time around, it's just a little bit different. Slightly different people, slightly different circumstances, slightly different outcomes, right? And so you could imagine, instead of a circle, an upward spiral, right? And each time you're on one side of the spiral, the same sort of thing is happening, but it's not quite the same as earlier or later repetitions. So you could think of each of the cycles in that case as a new universe. It's a new time around, a new attempt to see how things are going to turn out, and they're all just subtly different from each other. So that's potentially one way to think of a multitude of universes. We can also get the idea of multiple worlds from the concept of time travel, which we're all pretty familiar with today from science fiction. Unfortunately, physics says that it's probably not possible, but it's fun to think about time travel. And if time travel is possible, then it seems to indicate something strange about the nature of the universe. And maybe that there are many universes, and that time travel is really traveling between similar universes. All right, so first of all, that yellow line, think of that as the timeline of the universe, right? And then these smaller lines along it are individual people who are experiencing longer and shorter parts of that overall timeline. And they're all perceiving them from their own point of view. And so even if you have a singular universe, that yellow line, the long one, you still are going to have several different universes of experience, you might say. Every conscious being is going to experience the universe differently, and you could conceive of all of those universes of experience as being part of the totality. But from their own point of view, they're each a separate universe, and I can't really understand or experience your point of view, and you can't understand or experience mine. So in some sense, we're all living in our own universe. And so there are multiple universes in that sense. Now that's kind of fudging it, right? They're not really other universes. They're universes of experience. They're really all part of one universe. However, there are other ways to get multiple universes from time travel. So think of this as an example of the yellow timeline, right? Where at this time here, we have somebody who time travels. They go backwards to this earlier point in their own life. All right, now what happens then? Well, there's a couple of ways to think about this. And one way is to say that what's going on is that you're essentially creating a new branch of the timeline. Because after all, this whole period right here, I'm going to try to show it to you here, right? This period, right, in between your time of return and the time that you departed, right? All of that actually already happened before you left. It already happened. How could you change it? Well, one way that science fiction authors and physicists have conceived of this is that when you travel back in time, you're not really going back in time, or if you do, you're creating a branch of the universe, right? If you're not really going back in time, then what you're really doing is just jumping to another timeline, right? Another parallel universe, one that up to this point is exactly similar to everything that came before. But as they proceed, they're going to end up being slightly different from each other. Okay, so that's at least a possible way to think about time travel, is that since you can't travel, since you can't change the past, then if time travel is possible, then what's really going on is that you're going to different timelines. And a timeline in that sense is a whole other universe. So if you can do this, you end up traveling to the multiverse, or maybe creating the multiverse by time traveling. Now, if you don't say that, then there's a weird thing, right? Which is that this time, right, all of this time, from the time you leave to go to the past, right? If you go to the past, does the universe keep going on in green here, right? Do you still get all of that time, or is that entirely replaced? In other words, do you get a timeline that goes like this instead, right? Instead of this timeline over here continuing, you get the one up above it. That's a possibility. Time travel is impossible, so I guess anything could be the case, but that's one of the interesting ways to think about it. Just because we're talking about this, and I think it's interesting, let me mention some of the paradoxes of time travel. There's a thing called the grandfather paradox, which you might have heard of if you've ever read anything about philosophy of time travel or even watched some science fiction. The story goes like this, that if you go back in time to this point here, and you kill your grandfather before he meets your grandmother, well, that means that you won't have existed, right? Your grandfather doesn't go on to meet your grandmother here, and then have your parents, and then your parents have you, right? None of those things happen. And so that means that you don't exist. You never came into existence, and so you can't then go back in time and kill your grandfather. So killing your own grandfather creates a paradox, an impossibility. And some philosophers have argued that that means that time travel is going to be conceptually impossible, not just physically impossible. That's a damn shame from a philosophy of science, or sorry, from a science fiction point of view, because time travel makes for some really good stories. But you know, it might still be the case that time travel is impossible. There's another option besides the impossibility of time travel, which is that it's just impossible to kill your grandfather, or impossible to change the timeline. In other words, if you travel back and you try to kill your grandfather, you're going to slip on a banana peel just at the moment you're about to pull the trigger, or a truck's going to drive in front of him and your shot will miss, or whatever, right? So you just can never succeed. And so your grandfather will tell you these weird stories when you're a kid about how he kept having all these weird things happen to him at a certain period in his life, but then eventually he met your grandmother and everything was okay. And it turns out that you were the cause of all those weird events that your grandfather was telling you about when you were a kid. So you get a kind of a time loop here, right? You get you going back, you do something in the past that leads to this happening, then that makes you time travel, and you go back and you do that stuff, and right, you get this loop. All right, so there's some conceptions of this where if you do time travel, you are caught in an eternal causal loop. You never get out of it, and you're sort of isolated from the rest of the universe. The rest of the universe goes on without you. You're stuck in that little time loop, just repeating the same thing over and over again. Now, I'm not saying that's what does happen, right? Because time travel is impossible. This is just something that could happen if time travel is possible. Now, I guess that kind of causal loop is a new universe, right? It's not part of the original universe to have a causal loop in it. Now there is one. So you've created a new universe by doing what you thought was time travel. All right, well, let's leave time travel. Let's turn our attention now to time and special relativity. So now we're talking about other weird conceptual possibilities, but they're physically real, right? We know that special relativity and general relativity are highly confirmed theories, and basically we know that they're true. But the concept of time and special relativity is really strange, and it's a little bit hard to understand because it's so far outside of our own experience. These effects that I'm going to be talking about only appear for observers that are moving at very high relative velocities, or if you're in a very strong gravitational field. Nevertheless, these things do happen. Okay, so if it doesn't make sense to you, well, it shouldn't, because it's totally contrary to all of our experience and all of our intuition. But in fact, this is how time works in the actual universe. Now, this yellow line is meant to represent, this yellow arrow going upward is meant to be your progress from the past into the future. You can think of this yellow line as your timeline, right, with a time 0 at the beginning and whatever time it is now at the tip, and it's just going to keep going into the future until you unfortunately meet your end. All right, now the line that's perpendicular there, the orange one, represents the set of events that you take to be simultaneous. All right, now if two things happen at the same time, we say they're simultaneous, right? But Einstein's innovation in coming up with special relativity was to come up with a procedure for measuring when things are simultaneous. And what he came up with was this idea that, well, look, you could have a mirror traveling on a timeline or world line, as he called it, parallel to your own. right? And this mirror is at some distance from you, right? And you shine a light beam towards it, and you measure how long it takes for that light beam to bounce back to you. You could do this with a radar dish, for example. You could bounce a radar signal off of something. The same kind of idea. Now, I'm going to erase that line just so that we get less clutter on this page. It's already going to be pretty cluttered. So we'll just have to be patient and try to stick with it. So these red lines then are the light signals that travel out to the mirror, hit the mirror, and bounce back to your receiver. And you're carrying a clock with you in addition to a emitter and a receiver for these radar signals. Okay. Now, what Einstein says is that, look, you're going to make this inference that there's a certain total amount of time that it took, right? This amount of your timeline was involved in the emission and reception of that signal. And what you're going to infer is that since the speed of light is constant, right, the light was traveling at the same speed to the mirror as it was on the way back, and so halfway in between those two times, the time of emission and the time of reception, is the time that the light hit the mirror. Okay, so the mirror is at a constant distance from you, light's traveling at the same speed in both directions, and so the time that is halfway between the emission and the reception is the time that the light hit the mirror. So you are going to infer that that time, whatever that time was on your clock, is simultaneous with the time that the light hit the mirror over here. Now you can draw a line joining those 2 points, the line where the light hit the mirror and the halfway point on your own timeline. Draw that line and you get the plane of simultaneity, all of the things that happen at the same time as measured by you. So far, so good. Here's where it gets a little bit stranger. Einstein imagines now that we have another observer who's moving at some velocity pretty high compared to your velocity, right? You can represent the velocity as the slope of the line here. The light green line is tilted over to represent that this other observer is moving pretty quickly compared to you. Now, the observer is not moving at the speed of light. The speed of light is 45 degrees in this kind of drawing. So it's somewhere, halfway between 0 and the speed of light. Still pretty fast. Now, this observer is also going to do the same kind of reasoning. They happen to be at the very same place as you are, right, when you emit that light signal. And then they're going to be watching to see how long it takes for that light signal to bounce back to them. And they're going to say, oh, okay, well, here's the total time for me. Notice that that line is parallel to their own world line, right? And they're going to say that, well, okay, the halfway point for me is going to be when the light hit the mirror. So they don't see this other stuff out here, right? Nobody sees this. We infer that. That's not really the point here. The point is that what you see is that the light was emitted here and it was received here, and halfway between is going to be the time that you think that the light hit the mirror. So this is what we get. The world line O for the observer, the world line O prime for the relatively moving observer gives us 2 planes of simultaneity, the plane S for the observer O, the plane S prime for the observer O prime. Now you might not understand exactly what this is showing you. Don't worry about it too much. The point is that in special relativity, the order of events depends on your speed of motion compared to other people. Now there's no absolute speed in special relativity. It's only speed relative to some other observer. And if you're moving relative to that other observer, then you're going to judge a different order of events than they will. So that means that in special relativity, time order of events depends on the relative motion of the observers. Now that's really weird. That's way outside of our experience, right? Nobody ever has anything happen in their lives where this effect is noticeable. That's because it depends on having, oops, you might have heard my daughter running into the house. This depends on having very high speeds, which are not part of our ordinary experience. Some significant fraction of the speed of light is necessary before this effect becomes noticeable. Nevertheless, it's true and experimentally verified that in this framework, right, this event X out here happens before, according to O, this event X happens before the light hits the mirror. But according to O prime, this event X happens after the light hits the mirror. Nobody's wrong here. They're both right. They both have a different perspective. They just both experience the universe differently. Something happens before or after something else based on the state of motion. Now you might say here that each observer experiences a different universe because the order of events is going to be different. Now all of us have a pretty similar universe, right? Because for us, we're all moving at pretty much the same speed. We're traveling on the Earth through space. That's the largest component of our motion. So, you know, we are all experiencing time more or less the same. So we're not noticing events happening in different orders from each other. But if somebody were on a very fast rocket ship, then they would experience a different universe than we do, in the sense that the time order of events would be different than ours. Now, that's not really what people mean when they talk about a multiverse, but it is a way of thinking about there being different universes even in this one. The way around that is to say, well, look, if all of these observers know special relativity, they'll know the Lorentz equations, and they can convert between each other's point of view, so that in some sense they know the same thing. All right, they can explain from each other's point of view what the universe looks like. So there is one universe in some sense. It's just that it's a four-dimensional space-time instead of space plus time. All right, so instead of having space and time like Newton does, two separate things, for the Einsteinian special relativistic universe, we end up getting a space-time, a single thing. So instead of just having the three dimensions of space, now we add a fourth dimension of time, and that's where this idea of alternative dimensions comes from. So time is a fourth dimension, right? A dimension just means a direction along which you measure something. If you conceive of a cube, right, you get depth, width, and height. Those are all perpendicular to each other, and so that's what's called a basis for a measurement. Time is thought of as being perpendicular to all three of those dimensions. We call that orthogonal instead of perpendicular, just for technical geometrical reasons, but time is orthogonal to the three spatial directions. It's just a measuring dimension. Now, it's not static and absolute the way that it was in the Einsteinian universe. Instead, you can sort of shift things around a little bit with relative motion of observers. So you have to have all four dimensions to have the whole of the universe. So we have a space-time now. Now, in the early 20th century, people started talking about this other dimension, space or time, as another dimension. And they sort of thought, well, what if there are other dimensions beyond that? What if there's a fifth or a seventh or a 12th dimension? And unfortunately, in popular culture, and especially in science fiction, this idea of other dimensions came to mean something different than it really originally meant. It came to mean something like a parallel universe, a universe like our own, but not quite the same. Right? So those alternative universes that are similar, but not exactly the same as ours. So that's not really what a dimension was supposed to mean, right? But that's what it came to mean in science fiction. So if you read science fiction or watch any old movies, you might come across this reference to the fourth dimension or to the fifth dimension, and it's often going to be represented as if it's a whole universe, an alternative universe, but that's not originally what it meant. Okay, well, let's move forward a little bit to general relativity. And you'll recall from our discussion of the horizon problem, the concept of a light cone. So right here at the middle of the cone, right, is our observing point. And so what we can say is that our past light cone, the bottom triangle, right, is the set of all of the events that can have causally influenced us. And that's because the fastest anything can move is at the speed of light. And so if it would require it to be faster than the speed of light to impact us, right, if it were out here, say, that's a slope of greater than 1, so that's faster than the speed of light. This event over here is outside of our past light cone. And the same thing's true in the future as well. Things that are to the right or left of our future light cone are going to be things that we can't causally interact with. All right, so on the left here, I've drawn a bunch of white lines just to indicate this is a region that is totally outside of our experience. We can't have experienced it at this point that we're at right now. Okay, so from this point right here, all of this stuff out here is completely, utterly elsewhere. It's not in our past, it's not really in our universe. It's also not in our future. Okay, so this is stuff that we will never ever know. But presumably it's there, right? If there were an observer whose timeline had been over here, well, they would have intersected all of those things. And so for them, that stuff is in their past light cone or their future light cone. And so that's not the elsewhere to them, but then there's going to be things over here which are in the elsewhere of this other timeline. Okay, now this absolute elsewhere, right, is not the past, it's not the future, it's spatially separated from us, right? We just can't get there from here. So you can think of that as another universe, right? It's not really part of our universe, it's somewhere else. Now there's another way of conceptualizing it too, that it is part of our universe in some sense, because it's all connected across the bottom here, and so it is all one thing in one way. On the other hand, it's completely inaccessible to us. So functionally, it's as if that stuff were in another universe, and we just can never get there. We can never know what that stuff is like. So look at now these letters that I've drawn here, A and B. They're temporally separated, right? From B, you don't know what A is going to be, right? There is a temporal or a time-like separation between those two things. If you compare C and D, those things are spatially isolated. You can't ever get from C to D. Those two things will never know each other. Okay, they're just outside of each other's experience. Now there is a possibility, right, that this event here, right, will have a causal impact on us, but it can't at this time. It can only do that at this time. So if a signal from this causal event travels at the speed of light, it's going to impact our world line here, and then it will be in our past light cone, right? So what's really going on is that our light cone has just moved forward, right? There's more in our past now because time has gone by, and that event that was here is now in our light cone, right? Notice, by the way, that some things that were in the absolute elsewhere from the perspective of this position in our world line are now no longer in the absolute elsewhere. They're in our past light cone now. But there's still going to be a lot of other stuff out here that's still in the absolute elsewhere, and the vast majority of it is going to be stuff that we will never ever get to experience in any way. All right, so I want to think now about the horizon again. If you think about the Big Bang, right, and this surface, sorry, one second, let me erase that. This surface here, right, as the beginning, well, then you can be anywhere in the beginning, and from there move at the speed of light, right? And eventually you'll get to some point here. Now maybe that's the end of the universe, maybe it's some point in the far future, whatever you think it is, however you want to think about it, right? That's some end point. We call this time 0 for the beginning. Let's call this time, like right here, let's call that 1, all right? And so we've got time 1 here, time 1 here, time 1 here, and then another time 2 up here. It's very hard to draw with this pen, sorry. And then up here at the top is time number 3. Now at time 0, the whole universe is created, let's say. But then stuff starts happening, right? The universe evolves forward, and we get this situation. So we could talk about the regions that are red, yellow, and green. And at time 1, those regions, red, yellow, and green, are entirely separated from each other. They have never had causal contact, because to be able to move from here in the yellow over to the red would require moving faster than the speed of light, which is impossible. So these 3 regions, red, yellow, and green, are causally isolated from each other. This is the classic horizon problem that we talked about before. Now, as we move on to time 2 and eventually to time 3, more and more of these past light cones, red, yellow, and green, will be in common until you get to the time 3 when now everything from the red and the green and the yellow are all causally in contact with the apex of the light cone. All right, so these separate regions, the horizons kind of merge over time. But at any given moment in the history of the universe, there's going to be other regions out here, right? Even up here, this region or this region is not going to be part of the causal history of this point at time 3. So there are these other regions in the universe which are totally causally isolated from us. And there is a sense in which you could think of those as other universes, or at least other regions, right? Which are totally inaccessible to us. Those are the absolute elsewhere that we talked about a minute ago. Another way to think about that is, instead of taking the triangle of the side-on light cone, take the circle of the top-down light cone. So that region, that circle, represents the totality of the area of the original universe that can lead to this center point at some future time, right? So if that's the center, then it takes the speed of light to get there in the amount of time available. Well, what if we have some event, call it X, that happens near the edge of our horizon, right? Now we can't see anything out here, but there could be stuff out there, right? And it could in fact be that there is some other observer that has a different horizon than us, a horizon that includes X, but also includes a whole bunch of other stuff, including Y, that is totally outside of our horizon. We just have no ability to know about it. And there could be yet another observer that includes Y, but not Z, and so on, right? It could be an infinite number of horizons that are partially overlapping. And you could end up having an infinite universe, even though from our point of view, there's a finite boundary to our horizon. Now you could think of these regions out here as being, right, other universes. Okay, so those could be entirely separate universes, and there's another one over here, another one over here, right? Those are entirely separate elsewheres that aren't part of our horizon, aren't part of our universe. So these are mutually spatially isolated regions. They could exist. In fact, we have some reason to suspect that they exist, given the theory of inflation, the inflationary universe, that we've talked a little bit about in this course. Now, actually, in the inflationary cosmology, there's going to be exponentially more of these other universes, other regions, than there are ours, right? Ours is going to be an incredibly tiny portion of the totality. And in fact, it's an interesting consequence of some versions of inflationary cosmology that these different causally isolated regions could be quite different in their fundamental properties. So you might say, in some sense, it's all just one universe, right? All these different horizons are just different views on the one universe. And if you have infinite time, then those horizons are going to grow and grow until they merge with each other, until you have the whole of the universe in there. But at any given moment in the history of the universe, before you get to infinity, assuming that you have an infinite universe, there's going to be isolated regions of the universe that are not in causal contact with each other. According to some versions of inflationary cosmology, these inaccessible regions could have very different physics. The gravitational constant could be different, Planck's constant could be different, all kinds of different things could change from one region to another. So there could be different laws of nature in those other areas of this infinite space. Now that comes in handy when we get to the fine-tuning argument. The fine-tuning problem, as we mentioned in an earlier lecture, is that there are certain constants of nature, fundamental properties of the universe that you can measure, that seem to be very highly tuned, in the sense that if they were ever so slightly different, then life couldn't be possible. In fact, if you imagine changing the strength of the force of gravity, any change that's very much at all in the amount of time since the Big Bang would lead to either the collapse of our universe into a big crunch, or you would have enough gravity to form stars and galaxies. So it seems like we're in this very lucky little region where the actual parameters of the universe are almost exactly what they have to be in order for a universe like ours to be possible at all. Now, from a certain point of view, this seems like a very lucky coincidence. Right? It seems highly improbable that those parameter values would turn out to be exact to such a high degree. There's one calculation that was done in the 1950s or 60s which said that some of these parameters are fine-tuned to within 54 decimal places. So, that's probably not a good argument anymore. The inflationary perspective changes everything, really, but nevertheless, it's still going to be highly improbable that the parameters are exactly what they are. And anything that's highly improbable seems to demand an explanation. There's another issue, too, which is that according to the Copernican principle, or the cosmological principle, right, we're supposed to be, we're not supposed to have a privileged perspective on the universe. And you could extend that to say we shouldn't be in an extremely lucky situation where the parameters of the universe happen to be exactly right. It should be more like a random assignment of parameter values. And if it takes an extreme degree of fine-tuning, that seems like, at least according to some people's arguments, a violation of the Copernican principle. And so that would also require an explanation. Now, the anthropic argument was proposed as a way of getting around the fine-tuning argument in a way. Anthropos means human, and the anthropic argument is the idea that if the universe had different physics at all, then intelligent beings couldn't exist. In other words, we wouldn't be here to notice that the universe's parameters were different. So the very fact that we exist requires that the universe have these features. Now that's supposed to make it unsurprising that the universe is fine-tuned. It's a bit like evolutionary fitness arguments. From one perspective, you could say, wow, it's a super lucky coincidence that given that human beings need an atmospheric concentration of oxygen around 20%, that there's almost exactly 20% oxygen in this atmosphere. Whoa, that's a lucky coincidence, right? But in fact, there's a different perspective on it that makes the coincidence go away. And there's a natural explanation of it, namely that we evolved in an atmosphere that had 20% oxygen. And so of course we require that. If we grew up in a different atmosphere with a different oxygen concentration, we would have different needs or what have you. So it's not a surprise that our bodies require 20% oxygen. That's what we have in the atmosphere. That's how we evolved, right? So it's a natural thing that it turned out that way. So the anthropic argument is trying to do something like that for the cosmological parameters. Now it's not quite the same argument, right? Because it's not like the cosmological parameters caused us to exist. It made it possible that conditions could arise for us to exist, but that's a different sort of question. But it's meant to be a similar style of explanation. Okay, so we're supposed to be making it unsurprising that the universe appears fine-tuned, that the appearance of fine-tuning isn't really fine-tuning. Now, the basic anthropic argument doesn't require a multiverse. In fact, in the very first version of it, it didn't have a multiverse at all. But then multiverse thinking was inserted, and some people think that that makes the anthropic argument better. All right, so how does that work? Well, you can say this, look, if there is some sort of multiverse, whether it's that one that we talked about with regard to isolated regions that are different from ours in inflationary cosmology, or whether it's some other idea, right, where you have alternative universes entirely outside of our own, not related to each other at all. Presumably, if there are an infinite number of those things, then all possible universes with all possible arrangements of parameters exist. Now, most of them are going to be entirely devoid of life because most arrangements of cosmological parameters lead to a really quick recollapse or an infinite expansion and heat death and never forming galaxies or stars. And so almost all of those possible universes are going to be barren, devoid of life. But there will be some where the parameters are such that intelligent life can arise. And ours is one of them, right? So we can't exist except in a universe like that, so we're in that universe. All right, so you can see how combining the anthropic argument and the multiverse is kind of a natural idea. However, I don't think it really works, and let me explain why. We can get this sort of naturalness of our universe being fine-tuned and not really requiring an explanation, but only by speculating about the existence of huge amounts of stuff. we're not just speculating about a whole universe, we're talking about an infinity of them, right? And while we're not giving much detail about them, that's certainly a huge amount of stuff to have to introduce in order to explain our existence. Moreover, and this is really the key point, we have no evidence at all that these other universes exist. And so how can we use something that we have no evidence for its existence as a basis for an explanation about the existence of this universe? That seems to be a kind of mistake. Moreover, it's not just a problem of we don't have evidence so far. It seems like in principle, we could never have evidence about those other universes, precisely because they're other universes. They're entirely separate from ours. There's not going to be any signal that can travel between them, and so we'll never have any evidence that they exist. So the multiverse reasoning in the multiverse version of the Anthropic argument involves all of this speculation for which we can have no evidence at all. So it seems like it's not really scientific. It's just speculation. There's no reason to believe that it's true. Moreover, it doesn't seem to give us any significant explanatory advantage. Right? We're not gaining that much when we postulate an infinity of other entire universes. Right? We don't get that much. We already know that we exist. So why do we have to explain that existence with an infinity of other universes? There's a philosopher, David Lewis, who once described the metaphysics, not this one, but another one, as being promiscuous, right? It's too fertile, it's overly permissive, it's just bubbling over with new ideas and new entities and new laws of nature. And certainly the anthropic multiverse is one of those. It's overly promiscuous in that way. Now there are other problems with the anthropic argument too. I'm going to page through these pretty quickly. You can pause and read each slide if you want to. The main point is this first one, that we can't say that the anthropic argument is this one, that we exist, therefore the universe exists with these finely tuned parameters. And the reason we can't say that is that the causal order is backwards in that case, right? The universe pre-existed us, so it can't be our existence that causes the universe to have those parameters. So be careful. People often make that mistake when they're invoking the anthropic argument. Here's the second most important of these other problems. It says that we exist, therefore this is a universe in which it's possible for us to exist. But from the very fact that we are actual, we know that we're possible, so this really weak version or formulation of the anthropic argument doesn't do anything for us, right? It's not explaining anything. It's just repeating what we already knew. All right, so I'll skip over this. Let me turn now to quantum mechanics. You might have heard of the multiple worlds interpretation of quantum mechanics. That's relevant to our topic today, so let me just barely scratch the surface on this one. Quantum mechanics is really complicated, and we're not going to be able to discuss it in any great detail. But what we can say is that at the level of fundamental particles, right, atoms, electrons, quarks, and so on, reality is fundamentally probabilistic. There's a principle that says that you can't know both the exact position of a quantum particle and its exact momentum at the same time. Now you can measure either one to whatever degree of precision you like, but as soon as you measure one, the other one can only be known as a probability distribution. Right? So you could know the momentum of the particle exactly, but then its position is going to be just a probability distribution. You won't be able to know where it is exactly, and vice versa. Now there's a tendency to think that, oh, well, we just need more knowledge, and if we learn more, then we'll reduce the probabilities and we'll be able to get an exact measurement of both of those things. But actually that's ruled out by quantum mechanics. The universe is fundamentally non-deterministic, fundamentally probabilistic, so that those properties of position and momentum cannot both be known at the same time. Not just because of a lack of knowledge, but because reality itself doesn't have definite values of both. Now that's really weird, right? That contradicts our intuitions about matter entirely. That makes sense, though, because we've never experienced a quantum mechanical phenomenon in our ordinary experience. Now there are some phenomena that you can experience that are the result of quantum mechanics, but you're not experiencing the quantum mechanical effect itself. You're experiencing its observable effect. So the universe turns out to be not just weirder than we imagine. It's probably weirder than we can imagine, which is kind of a fun thought. But because it's so weird, it often is outside of our intuition, and we just can't make sense of it. So that's true certainly of most of quantum mechanics. You just have to kind of accept what the observations tell us, and that is that the universe at the quantum level is fundamentally non-deterministic. There's other ways in which we're dealing with non-determinism in quantum mechanics, including there are some events that happen with a certain degree of probability, right? Like a radioactive decay of a uranium atom, say. At a certain point, it will emit an alpha particle, I think it is, and then split into other particles. That's radiation or radioactive decay. And you know that over a certain period of time, it's likely that half of a sample of a radioactive material is going to undergo radioactive decay. That's called the half-life. But for any given radioactive particle, you can't know that it's going to decay in any time at all. It might never decay in the whole history of the universe, and it might decay in the very next moment. All right, so it's only a probability that we can attach to it. We don't know what when it's really going to undergo that probabilistic event. And again, that's not just a lack of knowledge, it's the universe being fundamentally probabilistic. Now you can measure those frequencies through careful quantum mechanical experiments. Okay, so we know a lot about this, and we've known a lot about it since the early part of the 20th century. It's always seemed weird, and people have always wanted to try to get beyond the weirdness and explain it away. But the most common interpretation of quantum mechanics is called the Copenhagen interpretation, because it was developed by physicists in Denmark. And it says essentially that we just have to ignore our intuition and just accept what the science is telling us. The probabilities are really in the world, they're not just due to a lack of knowledge, and we can't try to explain them away. However, that's never been perfectly satisfying. People have always found their intuitions just jangling against that, and so people have tried to come up with other interpretations of the quantum mechanical formalism. So what's going on here is that the Copenhagen interpretation leaves it purely a mystery why one thing happens rather than something else. That the uranium atom decays or it doesn't. Right? It ends up being just a brute fact that can't explain and we can't predict it in advance. And that seems unsatisfying to many intuitions. So the many worlds interpretation of quantum mechanics was put forward as a way of trying to explain away the quantum weirdness. But it does it with a really high cost. There's a very high price to pay in order to get that. And I think in the end it's probably not worth it. Now, let's just explain what the multiple worlds interpretation is. It says that all of these quantum mechanical possibilities are actual, but in other universes. And what we experience as, for example, radioactive decay according to probability is actually deterministic in this universe, but we just don't know why, right? But all those other possibilities really exist in other universes, right? So this uranium atom could decay now, or way later, right? And all of the possibilities in between really happen in some other universe. Now you can imagine then that all of the quantum mechanical things that are happening in a given universe are creating, every time there's a quantum mechanical choice or a probability distribution, then you end up with new universes. Right? So this is propagating universes like crazy. Anytime there's a quantum mechanical probabilistic event, new universes are created. There's really two options here. Right? This universe just keeps branching every time there's a quantum mechanical change, and then they all keep going, right? And they all persist forever. Or at least the way that this was originally described is that all the other branches fall off. So there's really only one universe in the end. But what does that mean, the branches fall off? That's a weird metaphor. And there doesn't seem to be a good reason to say that, well, those possibilities are real until one path is chosen and then they're not real anymore. That's pretty strange. So it seems kind of unsatisfying. Now, if this is the view you're taking, it's interesting to remember that in special relativity, the time order of events is different based on your state of motion. That means that the future has to really exist. Right? So we're not just talking about the universes that are now, But all the universes that are in the future, at least the ones that the futures you can reach by moving at very high velocities, all of those are already existing. And so you end up getting a kind of determinism out of this view, whereas quantum mechanics is supposed to be fundamentally indeterministic. So there's some weirdnesses here for sure. It's an extremely promiscuous metaphysics, right? It's saying that we have just so many universes being created all the time. I said here that there are trillions of quantum mechanical events per microsecond, but it's way more than trillions, right? It's probably trillions just in the room that you're in at the very moment. If you consider our whole Earth or the whole universe, there's just so many of them, all these events happening all the time. Not every quantum mechanical particle is experiencing one of these probability events at every microsecond, but a lot of them are. And for every one of those, as many universes are created as there are probabilities. So we're getting just so many universes being created on this model that the multiverse is just huge, and it's growing exponentially all the time. Now that's a creation ex nihilo problem that's way worse than the creation ex nihilo problem for the Big Bang, right? If you say the Big Bang comes out of nothing, well, what about all of these other trillions and zillions of universes that are getting created on the multiple worlds interpretation of quantum mechanics? That's one reason why people have said, well, the other branches fall off, to try to avoid that, but that's not a very convincing sort of ad hoc modification. Well, the same objections that we made to the multiverse anthropic argument can be made to the quantum mechanical multiple worlds interpretation. First of all, it's pure speculation, right? We have no idea whether or not those other universes exist. It requires a huge amount of unexplained creation. We don't know anything about those universes, and we cannot know anything about them. And it doesn't really seem to explain anything anyway. So it's a fun idea, but it's probably not correct, or at least we have no reason to think that it's correct at the current time. Well, that's sort of the end of the scientific version of multiverses. In literature, in science fiction in particular, we see lots of different kinds of multiverses, and I'll just mention a couple. I bet some of you have seen the movie Into the Spider-Verse, really funny movie, really interesting. That's a universe, that's a movie in which they imagine that there are parallel universes, right? They're not quite quantum mechanical multiverses, but they're similar, right? In that the universes are pretty much like each other with some very small changes. So there's a Spider-Man in each of these other universes, and they're just a little bit different from each other. Sometimes very different, right? Different color costume, or a different gender, or a different race, or what have you, but those are pretty small changes compared to the whole universe, right? Which is more or less the same. So in literature, we can imagine these other universes. And it's not quite the same as a multiverse cosmology or a quantum mechanical multiverse, because we're not imagining that every single possibility exists, right? We're just imagining that some of them do. And so there's some handful or a million different universes, whatever the number is, and they're all collected together into what you could call a multiverse. There's a book by Terry Pratchett and Stephen Baxter called The Long Earth that kind of has a similar idea, that there are very similar universes kind of right next to ours in conceptual space. And if you have the right technology, you can jump from one to the other. And it's a pretty interesting book. There's a series, 5 books. I think the first one is probably the best, but they're all pretty interesting. Well, what can we say about these literary multiverses? First of all, there's no constraints on them, right? They sort of just take a rough idea of the possible existence of another universe and kind of run with it and just speculate about what could be. And there's no particular reason to think that any of those actually exist. It's just fun to think about. Another kind of pure speculation about multiverses is something that I first encountered with a philosopher named John Leslie. He's one of the few philosophers to have made his whole career on philosophy of cosmology. But he did philosophy of cosmology with kind of religious orientation. That's a kind of thing that we'll get into a little bit more in next week's lecture. But for now, just let me mention that he thinks that there are an infinite number of divine minds, and that all of these divine minds are thinking all the time, and that everything that they think becomes actual. So whatever a divine mind thinks becomes an actual universe. So that's fun speculation, right? But again, we have no particular reason to think that those divine minds exist or that their thinking creates anything. We have no evidence of that whatsoever. But on top of that, Leslie just adds these weird ad hoc modifications like, well, we don't want these divine minds thinking of universes that are pure torture, so he says they only think the worthy universes. But that's just a silly assumption, right? How do you justify that? That's not something that has any basis in reality. So what I've suggested throughout this whole conversation about multiverses is that they're super interesting, but there's no basis for believing that they really exist. So there might be a possible world where it's sensible or rational to believe in the multiverse, but I'm sorry to say it isn't this one. All right, well, that's all for today. I hope you found that interesting. Let me know if you have any questions. Bye for now.